Hello again, everybody. I'm now here to talk to you about Aleo, so the shirt matches the talk. Again, I'm Alex, I'm the COO of Aleo, and I'm going to preface this talk by telling you that I'm going to talk about Leo, our programming language, and this is a high-level talk. The intention is not to be a deep dive into this. This is to talk about some of the features of Leo at a relatively high level. So if you expect this to be as good of a low-level deep dive into something like what Josh just talked about, I'm sorry to disappoint you. You should go get a drink right now and just enjoy that and watch or not. But anyway, I'm excited to tell you a little bit about Leo. So again, I guess before I tell you about Leo, I should tell you about Aleo. So okay, Aleo, wearing the shirt, what is it? So Aleo is a new layer 1 blockchain, and the focus is on building basically just a platform for private applications based on ZKP. What is the advantage of doing this versus something like Ethereum? So Aleo runs on the research is called ZEXE, so zero knowledge execution, was some research published several years ago that Howard co-authored, and he was up here a few minutes ago. And the idea is basically to take the Zcash model and extrapolate it to general programs, so not just simple payment transactions. So the advantage of this model, which I think Howard probably already talked about, so I'll run through these quickly, is program runtime can be unlimited. Effectively, you can prove something over however long you want and then submit that as a transaction. You're not limited by the block time of Ethereum. It's more efficient because you can prove something once, or you can prove something and then everyone just has to verify it once. They don't have to keep re-executing it over and over. And then you can kind of have a little bit of a flexible model in terms of how you want to execute a transaction. You can execute the proof yourself, or you can have a prover do it for you. And that enables you to have kind of a slightly more flexible model depending on the application. Again, the high-level idea, which I think applies to most projects building in ZK, which is one of the reasons why I'm excited there's so many projects building this space, is that the goal is to take this from being a technology that only PhDs or smart people like Luke know how to use, and down to something where maybe even Alex, I can use. That'll probably never happen. But generally speaking, it's to make it so you don't need a PhD in cryptography to take advantage of this technology. Okay, cool. I'm going to skip this slide. This is basically, there's a lot of parts to Aleo. Today I'm going to talk about Leo, though, which is our domain-specific language and compiler. Again, this talk is going to be high-level and relatively simplistic, almost offensively so I apologize in advance if that's going to bother anyone. But I'm going to start, so on that note, I'm going to start talking about, okay, what is a programming language, right? So programming language is basically this is a method to write a high-level idea, and then translate that into a low-level program. That's basically what a language and compiler does for you, right? Just machines execute code, ones and zeros, right? And that's obviously a little bit cumbersome to work in or to think in. And so you need some high-level language that somewhat approximates English or something else to write the idea, and then you compile it down to the machine code. So this is a Solidity contract. I pulled this from SafeMath, the ubiquitous the ubiquitous library on Ethereum, and this is the bytecode, also from SafeMath, so I pulled this straight off of Etherscan. Little known fact that I'm going to reference later, so Solidity compiles down to EVM bytecode, so that's what the two blue boxes are, but the little known fact is that there's an intermediate representation called UL that it can also target, and UL is kind of a lower, it's not quite bytecode, but it's a lower level representation of these ideas. So it's closer to what the machine actually executes, but it's not quite as high level as Solidity. And so a lot of people use UL because sometimes you can get more efficient by using that as opposed to Solidity. Okay, so high level language versus a low level language, the advantages and disadvantages. Again, this is quite high level. So high level language you can read, reason about, debug much more easily than something that's like machine code. A low-level language is, because it's obviously what a machine basically operates in, is going to be more efficient generally, but not always, right? And this is where compiler architectures come in. And I'm not an engineer nor a compiler engineer by any stretch of the imagination, but good compilers can sometimes make it so that high-level languages can be fast as, or sometimes even faster than if you hand wrote the machine code yourself. A good example of this is Rust. Right, where the Rust compiler can in some cases do optimizations to make it so that had you even just written this yourself naively, it wouldn't quite be as performant. So that's why those are the question marks on the bottom there. Okay, what is a zero knowledge proof? I'm looking around the room and half of you are I've been at this conference the whole time, and I've been waiting for someone to tell me this, and the other half of you are like, oh my God, I've heard this so many times, I'm going to throw up. And I'm gonna simplify this very greatly, just for the purposes of this talk, just to tell you what you quickly need to know. So zero knowledge proof. Okay, so actually I just pulled a quote. I'm not even going to tell you. I'm going to have someone else tell you, right? So there's proof systems, right, which is like the context in which these proofs are generated, and effectively, these proof systems consist of polynomials, right, that are represented as field elements of a finite field, and these polynomials represent some kind of circuit, right? So the top picture is an elliptic curve, which is basically it's a group, and then this lower picture is a circuit representation of a program. The proof, so the slide before, what is the zero knowledge proof? So the proof itself is actually just, in the case of a pairing based snark, is just a couple of group elements, curve points, and then the thing I wanted to highlight here, and this is a little bit of a side note or a little bit of a tangent, but some of you who may be kind of new to the space or new to zero knowledge are wondering, like, why, hey, Aleo and Anoma building their own new blockchains, like, why can't we just do all this on Ethereum today? And the reason I showed this picture is because you can see, like, this elliptic curve and the circuit, like, this is obviously like a different representation of a program than a typical computer would do. And Ethereum and the EVM is not really set up to encode programs in that way. So if you try and it's sort of like fitting a square peg into a round hole. So as a result, like, encoding programs on the EVM potentially results in gigantic circuits because of, like, the underlying cryptographic constraints. So just something to highlight. Again, neither of these are my quotes. This is actually straight from a great article that I will reference at the end and share the link to. Okay, so now what is Aleo and what is Leo, and how does this all fit together? So it's the high-level language, as we talked about in the beginning, is the idea for a program. So I want to prove that I know the sum of two numbers. I know it's a very silly example, but let's just go with it, right? And so you would basically convey that idea in Leo. You would write it, and then Leo itself would compiles down to the AVM, the intermediate representation. And the AVM does two things. The AVM is a layer that natively executes that logic, and so computes the answer, right? So you have to, in order to prove that the sum is equal to something, you have to actually compute it. So it does the native the program evaluation, and then it calls into SnarkVM, which is a lower level library in Aleo, and basically generates the program from which you can derive the proof. So that's how Leo, the AVM, proofs, and program evaluations fit together. And the important thing to highlight here is that as a developer on Aleo, you have the choice of whether you want to interact with Leo directly, so write in the high-level language, or go directly to the AVM and have lower-level control. So as I said, there can be advantages to doing it at a slightly lower level. It's slightly harder to debug and maybe reason about, but the advantage is you can generate proofs with less constraints potentially than you would, or programs with less constraints than if you were writing in Leo. And R1CS, for those of you who are not familiar, stands for Rank 1 Constraint System, and this is basically like the very low-level representation of zero-knowledge proofs. Cool. I have a couple slides about Leo. I think the thing I'm going to highlight here is one of the things that I'm really excited about is it's a language that we're formally verifying, and we feel this is very important because maybe I'll take a poll. Does anyone remember the bug in Zcash? There was a bug in Zcash. Zcash, for those, a couple of people remember, there was a bug that was discovered that would have enabled someone to mint an infinite number of Zcash. And it was discovered after the launch of the chain. And the thing that people kind of wondered was, well, did anyone ever take advantage of this bug? Well, because it was a private, it was a private cryptocurrency, you actually could never answer that question definitively. We think not, but because, private transactions, you actually have no idea whether or not someone did. And so the idea of formally verifying a language like Leo is to ensure that you're not, of course, you as a programmer can write a program with a bug in it, but a formal verification ensures that the compiler is not going to introduce a bug into your program that you wouldn't have otherwise expected. And I'm not going to get into formal verification in this talk, but it's something that not very many other languages have undergone, including in the traditional programming world. And again, something we feel very strongly about because, again, this contributes to the security of programs written on Aleo. Let me go back here. Yeah, the other thing we're trying to build with Leo, and this is a little bit separate from the AVM, is some kind of nice to haves that, frankly, I'm surprised more Web3 native programming languages don't include, which is stuff like testing frameworks, fuzzers, package registries, things that make the development experience easier on people who are familiar with programming in Rust or JavaScript or Python. So we're building all those in-house for Leo to hopefully make this as comfortable of an experience for a developer, particularly a developer who's used to coming from the web, the world of the web, and not the world of crypto. Because to us, the big opportunity is to onboard more web developers into the world of ZK and use that to grow basically the market of people, or the market for this technology. Cool. And so again, I think we highlighted earlier in the talk the difference between Leo and the AVM. But yeah, so this is just a quick summary about that. I think the key thing to highlight on this slide is that actually the on-chain representation of the program is the AVM bytecode. And so one of the unique things about Aleo compared to some other chains is that we have an on-chain basically namespace that maps program ID to program logic. And so that's what you reference as a prover. And actually, I think I have a slide on this. Yeah, perfect. So the way this AVM bytecode lives on chain, so you as a prover, you basically query the chain, get the bytecode corresponding to the program ID that you want to create a proof for, and you generate the proof. You can synthesize the proving key and verification key from those opcodes, generate the proof, wrap that proof in a transaction using Snark VM, and then transmit that transaction onto Snark OS, which is the blockchain. So you submit it to a node, and it propagates throughout the network. So that's basically the flow here for Aleo. And the other thing I want to highlight is that actually, as I mentioned earlier, the AVM can do both generate or synthesize the proof, but it also can handle native execution. And a mode that we're actually introducing in the future for Aleo is having this idea of a hybrid execution model. So for those of you who are familiar with the Zexi paper, it describes a model in which all of the computation is done off-chain, submitted as a transaction, and then verification is done on-chain. In this model, what we're contemplating is introducing basically a way, like we're thinking of calling it like a finalized statement, where you can write a program and have that program split into two parts. The part that you would prove off-chain, where a prover would prove entirely off-chain themselves, and then some logic that you want the miners or the validators on-chain to run, just like the Ethereum model. The advantage of this is that potentially you can manage applications that require concurrent state access more easily, right? So if you think about the most common example that comes up in this discussion is Uniswap. It's like, okay, how do you build a private Uniswap inside of a ZK Snark? Well, it's tricky because proofs by definition are generated by a single party, not a multi-party. It's not a multi-party computation protocol. And so you have this problem of like, okay, there's state that has to get concurrently updated over the course of a single block. So one way to do that is to basically, again, in our case, we have this effectively an EVM mode, which you can think of as a native execution of the AVM that validators execute directly, and it runs exactly like Ethereum. But alongside that, you can also have logic in the Zexi model too, and so you can maintain more privacy than you potentially could otherwise. And you can use this as a dial that you can basically decide how private or not private do we want this application to be. Because I think fundamentally in Aleo, we believe that like not every application or not every use case needs full privacy. There are some that certainly do, but different applications and different use cases, it may be kind of a middle ground. And so the idea is to give developers as much flexibility as possible to use to all the tools at their disposal to build whatever application fits their needs. The other thing I want to highlight is on top there. So we have Leo, like I mentioned, and that's what this talk has been mostly about. But the AVM is general, and we hope that as we continue to establish this and develop this intermediate representation, other people build languages or adapt other languages to target the AVM, and so give basically more ways to on-ramp into this ecosystem. Okay, before anyone gets mad at me for this slide, I didn't make this up, I pulled this from a talk from a YouTube channel you should all follow, which is the ZK Study Club, which I guess shameless plug, I help host with Anna Rose, the host of the ZK podcast. But this is from a talk by Alex Ozdemir at Stanford, comparing the various languages in the ZK space. So again, you take it from him, not me. And I guess like the key thing here is, Leo, we have support for primitive types. So, as I mentioned earlier, so zero knowledge proofs consist of group elements and field elements, and that is not typically the way computers effectively work natively. And so it takes a little bit of extra effort to support primitive types, so we support those in Aleo. We let users define their own types, which is nice for a variety of use cases, array access, if statements, mutable variables, and again, as I mentioned, it's the only language, not only in ZK, but actually I think in general in the last 20 years that's actually been formally verified. Cool, okay, what do we do with this? I'm sure this question's been answered many times throughout the day, but I'm gonna give you my version. What's ZK for, why do we care? Boiled down, these are the three things that I think are the killer use cases. So decentralized identity, my favorite example is the driver's license. Get into a bar proving you're 21 without showing your driver's license, because all the information on your driver's license is really irrelevant to the question of are you over 21, your address, for example. Shielded DeFi, which these days kind of extra important to prove you're solvent maybe without revealing your positions. I'm not going to name names here, but I think there's been a few large hedge funds and DeFi/CeFi firms that's been an issue for. But this would effectively let you have a proof to say like, okay, hey, I have a certain position or my portfolio has performed this well, but I don't need to show you or reveal its contents. So it's many applications in finance, to say nothing of the importance of being able to transact privately between parties. And then gaming. Gaming is a use case I'm extremely excited about. If any of you have not tried Dark Forest, you should absolutely do it. It's a really fun game based on zero knowledge proofs on Ethereum. Definitely worth checking out, and I think it opens up a whole new dimension of game mechanics that you can add on to and create basically a whole new class of games. And that's it. Thank you guys very much for listening to my talk.